So I'm going to ask, was the universe created? And we're going to look at it more from a theological science, plus science point of view than pure science. I want to start with the fundamental question about where do the laws of physics come from, because even though Lenny Susskind gave an absolutely beautiful talk which about the laws of physics, which gave us the possible explanation for the fine-tuning problem, the theists can still come back and say, yeah, but where did the laws come from? And so that's still going to be an issue. And of course, they say they came from God. And let's see if we can think of an alternative possibility. Now, that alternative that I would like to propose is that the laws of physics, in fact, were not handed down from above. I think it's our religious type thinking, Moses and the Ten Commandments, that leads us to think that the universe itself is governed by a set of laws handed down by God, or if most scientists would say, well, there must be something fundamental about the nature of the universe that gives us these laws. But basically, I'm arguing, and I would like to argue as an alternative, that the laws of physics are not restrictions at all on the behavior of matter. The laws of physics are human inventions, and what they are restrictions on the way physicists may formulate their mathematical statements about observations. And physics models, if they're going to describe an objective reality, have to possess a property which I will call point of view invariance. And this is a generalization of the work of Emmy Noether, who back in 1915 proved a very important theorem, and that is, for every continuous symmetry of the laws of physics, there exists a conservation law, and vice versa. So the most important laws of physics, conservation of energy, linear momentum, and angular momentum, can be said to follow from point of view invariance. She basically showed that any physicist who was, this is reformulating, she didn't put it in these words, I'm putting it in my words, that if you are a physicist and you are going to write down a model based on space and time, and you want to make sure that that model does not depend on any particular position, let's say position in space, moment in time, or direction in space, then that model will automatically have to contain these conservation principles. They're there. There's no avoiding them if you're going to have a model that has space-time symmetry, rotation and translation symmetry. In fact, if you extend the principle to 4 dimensions, and you allow rotational symmetry, you ask what's the consequence of rotational symmetry or rotational invariance in 4 dimensions, you get the Lorentz transformation, which means that special relativity just follows, again, from this principle of point of view invariance. So pretty much all of classical mechanics is right there because the laws of Newtonian mechanics follow from linear momentum conservation and so on. And so the idea is that gauge symmetry, which has been the principle behind the development of physics in the 20th century, up into, right through to the Standard Model, is a generalization of Noether's theorem from space and time to the spaces in which you draw your state vectors, as in quantum mechanics, that if you ask for point of view invariance, that's the same thing as gauge invariance, unitarity. A lot of these terms have mean the same thing. And so you can find that just about all the laws of physics, not every one, but quantum mechanics, for example, pretty much follows from this principle. So there's a conjecture that I'm making here, and that is that the laws of physics are just what they are because they have to be that way if the universe, in fact, came from nothing. If it came from a situation of absolute symmetry, then those are the laws that should exist, and there's no need for a creator to produce those laws. Now, that's a controversial, I'm starting out with this because it's the most controversial thing I will say. You could argue about it, but it is, I maintain a possibility. And even if you don't want to accept the gauge symmetry argument. And incidentally, I didn't mention that gauge symmetry has been known for 50 years. Local gauge symmetry gives you Maxwell's equations. You can derive them. And charge conservation follows from global gauge symmetry. So a lot of good reasons to believe that the Noether principle can be generalized to that situation. And I think a lot more work could be done on this to see how far it can go. Now, there's another argument that is common among theists, and I was surprised to hear Dr. Ross talk about it. This is an argument that's been going around for 30 years. Actually, it's based on an ancient argument from Aristotle and Aquinas. And William Lane Craig is a Christian apologist who has cast this principle in terms of an argument he calls the Kalam cosmological argument, make it sound like it has something to do with ism. But here it is. The argument is that everything that begins has a cause, and basically Hugh gave this argument today, and not in quite these words, but he said the same thing today. Everything that begins has a cause. The universe had a beginning, namely the Big Bang. Therefore, the universe had a cause. That's the Kalam cosmological argument. Now, there's a related argument that goes along with this, a related claim. It's based on the theorem of Hawking and Penrose back in 1979, that the universe began as a singularity. And Hugh mentioned that today, the universe began as a singularity. Well, Craig and other theologians have used that argument, saying, therefore, space and time began with the Big Bang, and there couldn't have been any before if time began with the Big Bang, and so only a supernatural origin is therefore possible. Well, let me refute those arguments. First of all, not everything that begins has a cause. This is familiar from quantum mechanics. Quantum transitions such as nuclear decays, atomic transitions that give you light do not have cause. They're unpredictable, at least according to the most common interpretation of quantum mechanics. Furthermore, the universe did not begin with a singularity. That the singularity theorem was tossed out long ago by both authors, Penrose and Hawking. And Hawking talks about it in his 1988 bestseller, The Brief History of Time. He kind of jokes about it. He said, I became famous by showing that the universe began in a singularity, and now I'm trying to convince you that it didn't, and the reason it didn't is because of quantum mechanics. The theorem wasn't wrong. The theorem was based on general relativity, but general relativity is not a quantum theory. And quantum mechanics has to come in at those very early moments. So the universe did not begin with a singularity, and therefore the universe need not have begun or had a beginning or a cause. No creator was therefore needed by those arguments. Now, what I would like to do is show you a natural scenario for the origin of the universe. This is based on the Hartle and Hawking model that was published in 1983, and I'm using a simplified version of it that David Atkatz showed back in 1994. Now I'm going to show some equations, because I want you to understand that this is a fully developed model. It may be a toy model because it may not have everything that every cosmologist would like to see, but it is a plausible model that I think closes the gap that you can't have a natural origin of the universe. Doesn't mean the universe actually began this way. As long as you can find one plausible natural explanation, you've closed that gap in the God of the Gaps argument. The principle is based on quantum tunneling. This is a very well-known process. You know that if a body has an energy less than the height of a barrier, it can't exceed that barrier. A dog can't jump a fence in the yard unless that he has enough kinetic energy to exceed the potential energy of that fence. But in quantum mechanics, where particles are represented by waves, you have a wave in this example here. As you see, there's a wave coming in from the left. It's a sinusoidal wave function that represents a physical particle. And then the Schrödinger equation, which gives you that wave, actually has a solution inside of the barrier, even though the particle inside of the barrier is unphysical. It has an imaginary momentum. It's not measurable. Theists are often saying scientists shouldn't be talking about things that are not measurable. We can talk about things that are not measurable. You can solve the Schrödinger equation inside the barrier, and you get the particular exponential type of function you have there. And you notice it leaks through, and then it becomes a physical particle on the right. Now, as I said, this is a well-established process. It's the explanation for alpha decay that was made by George Gamow about 50 years ago. It's the basis of the scanning tunneling microscope. So this, I'm not speculating here when I'm talking about quantum tunneling. And quantum tunneling is nice because it gives us a real concrete way of understanding the notion of a quantum fluctuation, which is a kind of a vague idea. You can think of the uncertainty principle of quantum mechanics resulting in an uncertainty in energy that enables the particle to jump the barrier. But quantum tunneling is something you can work out mathematically, and it's a lot more satisfying, I think. So let me just show you some of the equations, how you do this. The level here is about undergraduate physics level. You start out with the cosmological Friedmann equation, which is shown there. I'm doing this in one dimension. I'm assuming an isotropic universe, where A is the scale factor of the universe. Just think of it as the radius of the universe. And then there's rho, and there's the density rho, and Einstein's constant G. And then there's this parameter K that could be either +1, -1, or 0. Let me define A0 squared, and let me let K equal 1, which is the closed universe choice. And let me assume an empty universe. In that case, rho is just given by the cosmological constant. So that simplifies it there. And then you can solve that equation, and you get this hyperbolic cosine, that A varies with time as a hyperbolic cosine. And that's inflation. Now, it's not the familiar exponential inflation, but the hyperbolic cosine has two exponentials in it, and it gives us, in practice, the same result as exponential inflation. So there's the solution of the cosmological equation. That's all classical physics. But now what you can do is you can follow standard procedures in physics called quantization, which you use for going from a classical physics equation to a quantum physics equation, and you get what's called the Wheeler-DeWitt equation, which is given there, where psi is called the wave function of the universe. And again, this is in one dimension. I've simplified the problem by assuming a spherically symmetric universe. Now, it turns out that equation is just the Schrödinger equation for a particle of mass 1/2 and energy 0. I'm letting h bar c equal to 1, and that particle is moving into potential energy that's given by that equation on the bottom. Now, if not enough equations, there's the potential energy, VA, as a function of A, and there's two regions. There's a physical region outside, which is like that region outside of the barrier in the problem I showed earlier, and then there's this unphysical region inside, and inside the solution of the Friedmann equation is given there, but time is imaginary. So time is an imaginary number in the unphysical region, and so that means that's a region that we can't make measurements. That's, again, like the region under the barrier in the quantum tunneling problem discussed earlier. Now, what Hartle and Hawking did is they produced a solution. There are a number of solutions you could write down, but there's a no-boundary solution in which there are equal amounts of incoming and outcoming waves, and they look complicated, but you can fit it on a T-shirt. I mean, this is, after all, the wave function of the universe. Don't think that's complicated. That is as simple as you can imagine it. There's a region, again, there's the physical region at the top, and then the unphysical region, and I'll show you what it looks like. Here it is. Here's the wave function of the universe. Again, you see that oscillating part on the right, that corresponds to physical region where particles are real. And then you have this unphysical region, which is unmeasurable and has no structure, has maximum entropy, however you want to put it. And that's about as good a definition of nothing as you could come up with. Now, usually the solution they draw is something like this. Paul Davies had a similar picture today where they kind of, instead of the singularity at the beginning of the universe, this is a space-time diagram. Instead of a singularity there at the bottom, they kind of round it off. But there's another way, another possible solution that I prefer, makes more sense to me, and that's here. Again, we have, the shape is I think more accurate because it's exponential. You can think of that cone as a series of rings, the rings of radius A as a function of time, and it exponentially inflates. But there's a region where it starts out here that is nothing, the region where time is imaginary. And now, as I pointed out, and Sean also talked about that today, that there's no reason why you can't go back in time and earlier than the Big Bang. And so there could be another universe on the other side. You can think of that universe as tunneling into our universe. However, that universe has an arrow of time that points opposite to ours because entropy is increasing in that direction. In our negative time direction, entropy is increasing. So an observer in that universe would not observe a contraction, would be observing an inflation just like we do. So there's two mirror universes that come from the same point, come from nothing. So that's a worked out model. I gave you the mathematics, it's worked out. It's based on the best physics knowledge, and we could even calculate the tunneling probability using, this is textbook physics, incidentally, at the about sophomore level. And you calculate the probability for, I should say, what does the wave function mean? What does the wave function of the universe mean? I should have said that earlier. Basically, the wave function of the universe means that if you have an ensemble of universes, and you square this wave function, you square the amplitude of it, that's the probability per unit A that you will find a universe with that particular value of A. It's just like the meaning of a wave function of the hydrogen atom, same meaning. Now, if the probability of that transition is about 2/3, which means that if you call that physical region something and the unphysical region nothing, that something is twice as likely as nothing. And that helps answer another question, namely, why is there something rather than nothing? And let's see if I get to that here. Not yet, there's something else I wanted to say. And that is if you look at the entropy of the universe as a function of time, and I'm not showing the negative side of this, this would be just a mirror of this. The entropy of the universe increases with time, that's the red line, and it's always less than the maximum entropy. The maximum entropy of the universe would be a universe that was a black hole. A black hole of the same radius at any given time would give you the maximum entropy. The universe is not a black hole. But at the very beginning, at the origin, the earliest measurable moment, which is the Planck time, you notice the two curves come together. So the universe started out with maximum entropy, but it doesn't violate the second law because it was also minimum entropy. It was both the maximum and the minimum. And in other words, the universe was complete chaos, maximum chaos. And so that's why I say the universe contains no memory of a creator. If there had been a creator, there would have been no memory of it. Now that's of course subject to these pictures. The picture that the universe started out in a region very small of Planck dimensions. If it did, this wouldn't hold. But that seems to be our best knowledge of the present time. Now, that means that the only possible creator is, in fact, the creator that Einstein abhorred, namely the God who plays dice. And so, Nancy Murphy talked about the project to find a place for God to act in the universe. And I've read a lot of those papers from the Vatican study on that, and basically it seems to me that what they've come up with is just this. This is the only God that's really possible. First of all, he's not a theist God, he's a deist God. Most people in this country, 40% of the American people do not believe in the Christian God. They will say they're Christians, but if you ask them what God they believe in, what kind of God they believe in, it turns out to be a God who doesn't act in the universe, and that's the deist God. They don't know that, they wouldn't recognize the term deist, but that's what they really are. That's a recent survey from Baylor University. And the theologians who are trying to find a way to have God act in the universe without violating any of the laws of physics can only come up with this God, the God who started the universe out by playing dice and let it run its own way, and whatever happened, then as Kenneth Miller said, it doesn't matter. Whatever, if dinosaurs grew with brains and that was God's, it doesn't matter. It still fulfills God's needs. So in a way, you could still say this is consistent with the idea of God, but it's a God who has nothing to do with the Christian God, a God that doesn't answer. This God doesn't answer prayers, and certainly would not be worth praying to because he doesn't do anything. Now, let me get back to that issue of why is there something rather than nothing. First of all, why should 3 minutes? 3 minutes? Okay, thanks. Why should nothing be more natural than something? That's the first question. As I showed you, something is in that model, something is actually twice as likely as nothing. But there's no reason for something not being a more natural state of affairs. And one argument you could give for that is a familiar physics argument, that symmetric systems in physics tend to spontaneously undergo phase transitions to less symmetric systems in the absence of energy. And we have the familiar example of water, which is more random than ice. It becomes ice. If you leave it alone, if there's no energy present, there will be a natural, spontaneous transition that takes place. So there's a tendency in physics for simplicity to produce complexity, and nothing is more symmetric than nothing. So Frank Wilczek gave that answer back in 1980 when they asked him, why is there nothing rather than something? He said, nothing is unstable. Scientific American, 1980. Now, there's a question of fine-tuning. I don't have time to really cover this. There could be other forms of life. We've heard about multiple universes. Those probabilities that Hugh gave, I don't know how you go about estimating probabilities. Not all constants are constant, and the universe is really not all that fine-tuned for humans. Again, I would like to comment on something that Kenneth Miller said. He believes in God because there's so much order and out there, the universe is such an orderly place. Of course, he's a biologist. He sees order. If you're a cosmologist, you look out there and you see nothing but disorder. Most of the universe is entropy and very little order. There are just these tiny little pockets of order. So it's really not that fine-tuned. Besides, if God was perfect, why would he have to fine-tune the universe? Why would he have to twiddle a bunch of knobs to make the universe come out just right? He could make it right the first time. He's God, after all. Now, we talked about the constants of nature. Here's what the standard model tells you about the variation of the three constants. Notice they come together at some high energy. So the fine-tuning of those constants is just a matter of waiting in time for the universe to cool enough so they could differ from one another by a sufficient amount. I've also done my own simulations of universes by changing the constants of some of the constants of nature, and you can get, I've changed them by 10 orders of magnitude, and half of the universes come out with stars that have a billion years lifetime, so the lifetimes of stars are not particularly tuned for life. And I just would end with this quotation: "For God so loved the human race that he went to the expense of building 100 billion trillion stars and carefully shaped and crafted them for 14 billion years so that at this brief moment in time, we could all have a nice place to live. Now, I don't have him on this boogie board, but it's a quotation from my friend Hugh Ross. Thanks very much.